In the algorithms that we have seen until now, things happen in one phase. There is a problem, you get an input, and the algorithm solves the problem on that particular input. Now we are going to move to data structures in which things happen in multiple phases. The overall goal of data structures is to organize your data to support various queries using little time and space. As an example, consider an inventory. You have some items and the type of queries that you want to support are, for example, the following. You want to support a search. You want to know if some specific item is in your inventory. You want to support insert if a new item is arriving. And you want to support delete, for example, if an item is being sold or moved away. Let us start with perhaps the most basic example of data structures. Suppose that you're given n elements in an array A from 1 to n, and you want to support search. Given the array and an element, you want to know if the element is present in the array. There is a trivial solution, which is simply to scan the array A. That takes time, which is proportional to the length of the array A, which is n in this case. And this is the best possible that you can do if you're given both the array and the item X to search as input. Okay? But what happens if we are first given an array A and we are allowed to pre-process the array, so to perform some computation on A? Then can we answer the search queries faster? How would you pre-process the array A to answer such queries faster? Well, you can, for example, as a pre-processing step, sort the array. So you can sort the array. This takes time order of n log n, a space order of n, but this just happens in the pre-processing phase. Then each query search can be answered via binary search. Okay? If you want to search for X in array A, which is now sorted, okay? If the array has length 1, then I just check if the element is X, and otherwise I pick the mid element of the array. If it's less than X, then I can search from the right half of the array, and otherwise I can search in the left half of the array. And the time for this, because we divide the length of the array into each time, becomes order of log n. Now, can we do even faster than this? This is such an important problem to search items. There are in fact some very ingenious solutions, and I just want to mention now a simple solution which works in a case in which the items are small. Okay, let's make the further assumption that my elements are all at most k. Then can we do faster than log n? Okay, and in fact we can have a very simple algorithm which is extremely fast. Okay, we use a technique which is called direct addressing. Okay, so we're gonna keep an array S with k elements, which is initialized to 0. And then we're simply going to set to 1 the positions which correspond to elements in A. Okay, so for I that goes from 1 to n, we're going to set the AI entry in S to 1. So the array S tells us which elements are present. And all this thing happens in the pre-processing step, takes time order of n, a space k. Okay, so the space is small as long as you have the assumption that the numbers are small. Now, the cool thing is that search can be done very fast. How fast? Well, it can be done in constant time, right? if you want to know if the element x is in A, I can just return s of x. I just go and fish the right location in the array s. Okay? And this just takes constant time. Okay? So this is a very simple solution with an extra array, an extra table. But it's very important to keep in mind that if you have assumptions like the numbers are small, you can do such things. Okay, so far we have considered static search. Okay, we preprocess the array and then we want to search, and that's it. And for the inventory example, we actually have to consider dynamic search. Okay, so you want to search and also insert and delete. So let us see what we can do in that case. So now let's say we want to support the search, insert, and delete. Okay, and again, let's see what we can do if the numbers are small. Okay, to build intuition. Okay, if the numbers are small, you can preprocess the array s to 0. Okay, and then like before, if you want to search for an element, you just return s of x. And insert and delete are also extremely simple, right? If you want to insert, you just set the right location of the array s to 1. If you want to delete, you set it to 0. So the time for this is constant per operation, and the space is order of k. Okay, so if you just want to do this basic inventory with small numbers, you can do it in this very efficient way. Now, what happens if the numbers are not small? Okay, if you're working with keys of arbitrary length. In fact, there exists a whole industry of data structures which deal with this case. Okay? And they are mostly based on trees. So the first one that was invented was the AVL trees. Then there are 2-3 trees, 2-3-4 trees, B trees, red and black trees, AA trees, left-leaning red and black, and so on. Many examples. And there is even structures of a different type which are very common, like skip lists, which are randomized, and deterministic version of a skip list. We're going to spend some time understanding the AA trees, but before we get there, let's just see some background on binary search trees. Okay, so a binary tree is an object like in this picture. So it has a bunch of vertices, also known as nodes. In this case, the nodes are A, B, C, D, and so on. There is a root node. In this case, the root is A. Each node has a left subtree and a right subtree. So the left subtree of the root is C. The right subtree of the root is this subtree here with the green circle. You can also ask for what's the parent of a node. So for example, the parent of B would be A. Okay. The leaves are the nodes with no children. So C is a leaf, F is a leaf, I is a leaf, H, and D. And we also care very much about the depth of the tree, which is the length of the longest path from the root to a leaf. Okay? So in this case is 4 because it's 1, 2, 3, and 4. So it is possible to represent trees using arrays, okay? And I just want to give you a concrete example so that you have something to keep in mind, okay? If you have some doubts about how exactly the parent is stored or the children are stored, here is how they are, okay? So here is a tree, okay? And I can represent it with an array, in fact with several arrays. So here is just the index of the array. So the arrays will go from 0 to 5. I have one array for the keys, okay? So for example, in the 0 position of the array, I can put this node here, which has the key A. So I put A here for key. In the 1 position of the array, I can put this node here, which has key D, and so on. Then I have another array for the parent. So for example, the node at position 0 has parent the node at position 4 in the array. The node at position 1 in the array is this, and has as parent the node at position 2. The node in position 2 has as parent the node in position 4, and so on. The root, which is in a position 4 in the array, has a special entry for the parent. We can call this null. It means it does not have a parent. And similarly, you have left child and right child. So, for example, the node at position 3 has as left child null and as right child null again. The node at position 5 has as left child null because it does not have a left child, and as right child would be a 3 because it's this node here. Okay. You also have to keep track of who's the root, so you have a special variable called root, which in this case is 4, and you also want to know how many nodes you have in the array, so you can have a variable called numNodes, which points to the right. Actually, in this case, it should be 6 and not 5. Okay, so we have 6 nodes here. This is thing is a typo, should be a 6. Okay, these were just trees. We care about searching, as we just saw. So it is natural to think of how you can use the trees to search. Okay, and a binary search tree is a data structure, okay, where the data is stored in the nodes of the tree, and the data is referred to as the key of that node. Okay, so this was just like before, where the keys were H, F, D, and so on. The important thing of a binary search tree, which is what makes it different from just a binary tree, is that it satisfies the binary search tree property. Okay, the binary search tree property says that if you have a node, okay, the keys which are in the left subtree of that node are smaller than the key at that node, smaller or equal. So for example, this node here at 7, in the left subtree you have 5, 4, 6, 5, and 7. And on the other hand, the binary search tree property says that in the right subtree you must have bigger keys. So here you have, on the right subtree you have 9 and 8, which are bigger. Once you have a binary search tree, you can search using the tree search operation, which is similar to binary search. Okay, so if you're looking for a key K in a tree which has root X, okay, you start at X. If X has your key, then you're done. Otherwise, if X is less than the if K is less than the key at X, then you continue your search in the left subtree. This is what happens here. You do tree search on the left child of X, and otherwise you continue your search on the right subtree. Okay. If you finish the tree and you don't find K, that means the K is not in the tree. The running time of this operation is proportional to the depth of the tree. Okay, this is very important, proportional to the depth of the tree. So if we are lucky and our tree has a very small depth, like depth is order of log n, then the search time will also be order of log n. If the tree is very bad in some sense, has a depth maybe n, then the search time will be much lower, n. So tree search is really a generalization of binary search in an array. Okay, so a sorted array can be thought of a tree which is very balanced. Okay, so every node has 2 children, and that will correspond to a sorted array. Why are we using trees instead of arrays? Is because the trees make it easier to think about inserting and removing items. Okay, let us see how we can insert a key k in a binary search tree. Okay, here is the pseudocode. Okay, at the beginning we can check if the tree is empty. Okay, if the tree is empty, then we simply create a root with a key k and return. Otherwise, what we do, we basically search for the key k in the tree. Okay, so we're going to search for k in the tree, and at some point the search is going to end. Okay, assuming that it does not find the key k. And when it ends, you were at some node y. Okay, so y is the last node that you visited during the tree search for item k. Now, if k now has value which is less than the key in node y, then we can insert a new node with key k as a left child of y, and otherwise we insert it as a right child of y. Okay, the running time of this is dominated by the time to calling tree search, which, as we saw earlier, takes time proportional to the depth of the tree. So again, if the depth of the tree is order of log n, then the insertion time also would take time order of log n. Okay, let us give an example of how insert works. Let me do it here so we have the codes on the same page. Let's say we start with the empty tree. Okay, and then we insert keys 1, 5, 2, 8, 3. Okay. So what happens? Okay, at the beginning the tree is empty. I want to insert key 1. Okay, so I'm going to create a root with key 1, and I'm going to return. Okay. Then I want to insert a 5. Okay, so I'm going to search for 5. The last node which I visit is 1. And 5 is bigger than 1, so I put my 5 here as the right child. Then I want to insert 2, so I search for 2. So searching for 2 means that you start at the node with key 1 at the root, then you go right at the node with key 5, and then you stop there. 2 is less than 5, so you're going to put a 2 as a left child of 5. Then you have an 8. Again, you search for 8. You start at 1, you go to 5, and then you stop, because 8 is bigger than 5, but 5 has no right child. So you're going to put 8 here. And finally, if I want to insert 3, I search for 3. So I go from 1, 5, then I go to 2. I stop here, and I'm going to put 3 as the right child of 2. Okay, so this is how the operation works, and we have just seen the pseudocode, and we can also give the code in more detail using our representation of a tree as an array. And here is how the code would look like. Okay, and here is our representation of the array of the tree as arrays. The number of nodes is num nodes, as we discussed earlier. So num nodes points to the next entry to be filled in the arrays. So the first thing that we check is whether num nodes is more than the maximum number of nodes that we want to have in the array. If so, you're done. Sorry, you cannot insert anything else. Otherwise, what we do, we start immediately and we put a new node. So we fill this position here. Say if this is the entry for the keys, you put a key here, a key K. And as left child and right child, you put null. Okay. Okay, and what remains to determine is the parent of this node. Okay. So in case the tree is empty, then there is no parent. Okay. So if there is no nodes, then the root just becomes this new value, and the parent of my node is null. Otherwise, what we do, we search for the parent. Okay. So we go very similarly to the tree search routine. So we start at the root. And then how do I know if something is a parent? Well, something is a parent, x is a parent if k is less than the key of x, but x has no left child, okay? That would be the last node that you see in the search. If that's the case, you set as left child this new node that you just created, and as parent of the new node, you put x. You increase the number of nodes and you're done, you return. You have a symmetric code in case it's the right child instead of the left child. And otherwise, you continue the search. Okay, so if k is less than the key of x, and you can go to left child, then you continue to left child. You set x to left child of x, and otherwise in the other direction. So this concludes the more detailed code. This code is important to give you a more concrete sense of how you operate with trees using arrays, because ultimately what's going to be in the computer is this, is the array, is not a tree structure. The tree structure is more in our head. So if you want to know exactly what's going on and the time of operations and what kind of things you can do and you cannot do, it's good to go back to such code and to see this code at least once in your life.